What is an app service instance? An app service instance is basically a virtual computer running a managed OS, running your web application code, but you never see or manage the OS directly. Think of it as a computer that Microsoft owns, but you rent a slot in it. It has CPU, RAM, networking, storage, file system, process scheduler, security patches, just like a normal server. But you do not SSH or RDP into it. In my app, it's actually managed by Microsoft. As Azure manages the OS, kernel, firewall, etc. And they also charge you for that because they manage them. What OS does our service actually use? Two choices. If you deploy .NET or C, it's using Windows Server. If you deploy Node.js, Python, PHP, or Go, it's Linux or Ubuntu based. So yes, it is literally a real operating system. What does your code look like in there? Inside one app service instance, you have operating system, Linux or Windows. Then underneath you have kudo/web job host or IIS or Nginx orchestral. Then under it you have your web app code. So it is very much like someone's computer in the cloud running your web app. Is one instance a computer? Yes. Cloud terminology translation. Cloud term. One app service instance, what it really is, one rented computer running your app. Cloud term, scale out to 2 instances, what it really is, your app now runs on 2 computers. Cloud term, CPU or RAM usage, what it really is, the VM's actual hardware usage. Cloud term, pricing tier, B1, S1, P1, V2, what it really is, size of the virtual machine. Example, B1 plan, 1 CPU core, 1.75 gig RAM, just like a small laptop. So why run 2 instances instead of 1? 3 real and practical reasons. Reason 1, high availability, no downtime. If you have only 1 instance, user clicks, that machine responds. If it crashes, site is down. With 2 instances, machine A crashes, traffic automatically moves to machine B. User never notices. Cloud providers do not give 99.9% uptime SLA unless you have at least 2 instances. Reason 2, more performance, more requests at same time. Imagine each instance can serve 200 users at once, but payday hits, 2,000 employees log in at the same time. With 1 instance, it chokes. With 2 instances, traffic spreads. 1,000 to instance A, 1,000 to instance B. Result, faster response, fewer timeouts, smoother peak payroll days. Reason 3, rolling deployment, no downtime updates. Suppose you push a new version of the app. With 1 instance, site goes offline while updating. 2 instances, system updates one at a time. Instance A updates, traffic routed temporarily to instance B. When A is ready, update B. User sees 0 downtime. How do requests choose which instance? A load balancer in front user to load balancer 2, instance 1 or instance 2. The load balancer chooses based on round robin, list connections, performance telemetry, session affinity. Users may hit either machine. Does the backend and frontend run on the same instance? Three common setups. A. Classic monolith, both together. Front end, back end running in one app service. Also, this load balancer are actually chooses how it will prioritize the instances, kind of like in operating system. It could be round robin, multi-level feedback queue, list connections, performance telemetry, etc. So the classic monolith is okay for small SaaS or side projects. Separate web plus API app services. App service 1, Angular static site. App service 2, backend REST API. More scalable. Containerized Docker. Each instance may run front-end container, API container, worker container. Kubernetes schedules them. So for containerized Docker, you might have a container for your front end, container for APIs or back end, container for worker. So these are more scalable than classic monolith. How does CPU RAM this work? Each instance has its own limit. Example B1 plan. CPU 1 vCore, RAM 1.75 gig, disk 10 gig. If your app uses 900 millibytes, that is within the VM, not shared with others. The VM is dedicated to you if you auto scale to 4 instances. You now have 4 CPUs, 4 times 1.75 gig of RAM, 4 times storage allocations. So that's how you auto scale if you have those computes within your instance. You are effectively renting 4 small computers. What about database? Azure SQL 2 vCore. Is that also a computer? Yes, Azure SQL, Azure PostgreSQL, Azure MySQL. All of them are managed database servers running on real VMs. 2 vCore literally means it has 2 virtual CPUs assigned. And storage, memory, OS, patching, security are managed by Microsoft. So it's actually being managed by Microsoft if you have this Azure MySQL, Azure SQL, Azure PostgreSQL. In my app, I actually have Azure SQL. So 2 vCore literally means it has 2 virtual CPUs assigned on that computer using that managed storage. And storage, memory, OS, patching, security are managed by Microsoft. You do not log in and install PostgreSQL manually, but you pay more because they manage it, they install it, they manage the software update, etc. But in my app, I'm on free tier, that's why I don't have any payment. Are app service instances separate computers? Yes, visualized instance 1, VM number 1031, instance 2, VM number 2055, instance 3, VM number 3011. They run identical copies of your app deployed together. If you have 2 instances, your code is deployed twice. Memory is separate, CPU is separate, threads are separate. Just like you run the same program on 2 laptops. Step 1. What ifconfig is showing. When Linux prints bcast 10.0.0.127 mask 255.255.255.128, it means your interface is on subnet 10.0.0.0/25. So they chose it. Or the subnet basically are inside that where the broadcast is 10.0.0.127. Whenever you have this broadcast address and you choose that as your someone you want to ifconfig, it means you're in the subnet 10.0.0/2025. The host bits are 7 bits because /25. All host bits equal 1 gives the broadcast address. 10.0.0.0 or 0.0.0.127 equal 10.0.0.127. So 10.0.0.127 is the IPv4 broadcast address for this subnet. This is layer 3 IP. So that's the layer 3 IP that you will use to map it to the layer 2 broadcast MAC address. What happens when you ping the broadcast? So if you run ping 10.0.0.127, the OS constructs IPv4 packet, source IP equal 10.0.0.13, destination IP equal 10.0.0.127. So it has your source IP and it will now have a destination. It will encapsulate that. But now IP needs a layer 2 next. Hop MAC step 3. ARP lookup is skipped. Normally for unicast, IP needs MAC. It will send ARP query, learn MAC, then send frame. So usually once you have that layer 3, it will send an ARP query to that to be able to learn MAC or to know the DST MAC, learn MAC, and then before it send frames. But for broadcast, Linux already knows, so this packet must go to all hosts on the LAN, so it does not ARP. Instead, Linux immediately uses destination MAC equal FF, the 6FF, which is the Ethernet broadcast address. Step 4. The packet gets encapsulated. Encapsulation looks like this. Ethernet header dest MAC equals 6F for broadcast, SRC MAC equals 00:08:74:93:C8:3C, ether type equals 0x0800. So these are the parameters or the properties of the 10.0.13 source IP. And in IPv4 header, we have DST IP equal 10.0.0.127, the subnet broadcast, SRC IP equal 10.0.0.13. So IP broadcast is carried inside Ethernet broadcast. Step 5. What happens on the LAN? Every NIC on the LAN receives the frame because MAC has 6F matches the hardware's broadcast filter. So it matches the broadcast address of each MAC or NIC on the LAN. That's why they receive that. Then NIC interrupts CPU, OS receives frame, and then decapsulate or demultiplex the IP. IP stack checks if the IP destination matches. Then if it is this system on subnet 10.0.0/25? If yes, it will deliver packet to ICMP handler, since that's an IF config. So that's how the OS are designed to work. So since it's from 10.0.0.13, which is within the subnet, the machine will not gonna ignore it. So if the machine is outside the subnet, it will ignore it. How do they connect? IP broadcast says which host should logically receive the message, i.e. 10.0.0.127. Ethernet broadcast says how to physically deliver the packet. IP needs Ethernet to carry its packets, and Ethernet doesn't understand IP addresses, only MACs. So the mapping is IP broadcast address to encapsulated in MAC address frame. Let's explain the sentence. The text is showing how Linux computes the layer 3 broadcast 10.0.0.127. When you send the broadcast ping, the OS automatically sends it to Ethernet MAC 6F. So ifconfig is showing layer 3 broadcast. Ethernet uses layer 2 broadcast. One wraps inside the other. So the ifconfig shows us the layer 3, and then the Ethernet uses layer 2 broadcast from that layer 3 mapping, and then one wraps inside the other to be demultiplexed on the receiving OS. To see how simple broadcasting works, we can send an ICMPV for request message using the ping program to the broadcast 10.0.0.0.127 indicated by the output of the ifconfig command. So here's a Linux ping -b 10.0.0.127. We mentioned in chapter 8 that in this type of broadcast, all the hosts on the local LAN or VLAN are affected. Here, we receive replies from 3 other hosts on the network, and the ping program notes that the more responses we receive than the number of requests sent, so the dupe. So if you receive more than the number of requests, you're gonna receive dupe, which is a normal expectation since it is a broadcast and it is within a subnet that has more than one host. 10.0.0.127 is the layer 3 IP broadcast address. So from the config output, we have enet addr colon 10.0.0.13 bcas 10.0.0.127 mask 255.255.255.128. This means subnet colon 10.0.0.0/25. Host bits is 7 bits. All host bits set to 1 equal broadcast. So at layer 3 IP, any packet sent to 10.0.0.127 means deliver this packet to all hosts on this subnet. So anything in the /25 subnet will receive that ping. So you send a broadcast ping -b 10.0.0.127. Linux warns you warning pinging broadcast address because this packet will be visible to every host on that subnet. So now Linux create ICMP echo request destination IP 10.0.0.127 which will be mapped to the broadcast to their broadcast MAC address with the source 10.0.0.13. IP needs to deliver the packet over Ethernet. IP now asks, what MAC address should I use to send this? For a normal unicast destination, it would send an ARP request. But this is broadcast. So usually to get the MAC address of its unicast destination address, it will send a MAC ARP request since normally it's an IPv4 subnet. But since it is a broadcast, Linux already knows. So broadcast IP must use Ethernet broadcast MAC. It encapsulates the packets like this. Ethernet frame destination MAC equals 6F, layer 2 broadcast source MAC equals the source MAC of 10.0.0.13, ether type 0x000, the IPv4. So here's the connection. 10.0.0.127 layer 3 broadcast to 6FF layer 2 broadcast. IP broadcast carried inside Ethernet broadcast. Every host on the LAN receives the ping because 6F matches the hardware broadcast filter in every NIC. Each computer on the subnet sees the packet and checks, is this destined for a subnet I belong to? If yes, pass to ICMP handler. Each host responds individually unicast. This is why the ping output shows 64 bytes from 10.0.06, 64 bytes from 10.0.0.113 dupe, 64 bytes from 10.0.0.120 dupe. Broadcast request, multiple unicast replies. And dupe means there are multiple replies to the same ping sequence number. So you only initiate one request but you receive multiple replies, which is expected. How this example connects everything? This single command demonstrates layer 3 IP action packet sent to an IP broadcast address 10.0.0.127. Layer 2 Ethernet address using Ethernet broadcast 6F hardware. NIC is delivered to the frame to every host. ICMP, every machine replies with a normal unicast echo reply. This is a real-life demonstration of how IP broadcast maps into Ethernet broadcast, how multiple hosts receive the same frame, how you can visually see it happening. The important conceptual link, the IP address 10.0.0.127 means all hosts in this subnet should receive this packet. Ethernet MAC 6F is send this frame to all NICs on this link. The OS performs this mapping automatically. So the ping example shows the entire chain working live. Ping command to IP packet sent to a broadcast IP, then encapsulated in Ethernet broadcast received by all hosts. All hosts respond individually, which is why you get duplicate requests. To see addressing being used, we can investigate the action using Wireshark. See figure 9.1. So we have echo ping request, and you can see we have 3 replies. So time FIP packet 678. An ICMP v4 echo request message sent to the directed broadcast address on the local subnetwork is encapsulated in a link layer broadcast frame with the destination address of all ones. The echo request message is sent to the address 10.0.0.127. The IPv4 implementation determines this to be the subnet directed broadcast address by consulting information in the local routing table and interface configuration information. Remember in the previous video how the IPv4 implementation already know or determines the subnet directed broadcast address by consulting information in the local routing table, because that router has a memory. So it's saved there that it is from a broadcast address, and it knows that it's from /25 subnet. Therefore, it's just map it to its broadcast address. By consulting information in the local routing table and interface configuration information, and it sends the diagram using the link layer broadcast address 6F. So no ARP request is needed to determine the MAC address for each destination. In fact, the sender is unaware of what host will respond until they do. So it doesn't need to be responded via ARP by its unique address until it receives reply, just like this in Wireshark. It knows only that 10.0.0.127 is a broadcast address, and that it should therefore use a broadcast link layer destination address when sending. The source addresses at both the IP and link layers are entirely conventional unicast. Multicast addresses are used only as destination addresses. In this particular example, notice that each of the responses generated is directed at 10.0.0.13, the unicast address of the original sender, and that each response includes the IPv4 address of the responder, 10.0.0.6, 10.0.113, and 10.0.0.120. This is a simple example of a more general principle, broadcast addressing and multicast addressing, as we shall see shortly. Can be used to discover system or services that are otherwise unknown. In this example, the outgoing broadcast ping request discovered 3 hosts that are willing to respond to broadcast echo request messages. So because the NIC supports their broadcast and the ICMP kindly map it to the MAC broadcast address, we were able to find hosts that we would not otherwise find. So this is how we use that every day. This is how we ARP our router MAC address using laptop, etc. Or this is how we find devices near us. Sending broadcast datagram. Generally speaking, applications using broadcast use the UDP protocol or ICMP v4 protocol and invoke an ordinary set of API calls to send traffic. The only exception is that when invoking the API calls, a special flag SO_broadcast is used in some operating systems to indicate that the application really does intend to send broadcast datagrams. For example, in Linux, failing to use the -b flag when attempting to do a broadcast ping uses the following output. Ping 10.0.0.127. Do you want to ping broadcast? Then -b. This error is caused by the SO_broadcast flag is provided through the API only when the -b option is provided in the command line. This helps to avoid accidentally generating broadcast traffic that could temporarily congest a network. So you need to put -b to avoid accidentally generating broadcast traffic that could temporarily congest a network. To determine which interfaces are used for broadcasting, the IPv4 forwarding table, just like how the IPv4 were used before to map what the broadcast address, or to map it in memory what's the broadcast address. It also does that to determine which interface are used for broadcasting, called routing table. The following is an example of a Windows Vista routing table. Later version of Windows used an identical format showing that interface list and broadcast related routing information. Other information has been removed for clarity. Netstat-rn interface list, we have number 10, 9. So Microsoft loopback adapter for 9. You have this MAC address for Intel R Pro wireless network connection. For 8, Broadcom integrated controller. For 1, software loopback interface. For 12, Microsoft eSATAP adapter. Number 13, Microsoft eSATAP adapter number 2. 11, eSATAP as well. IPv4 route table. We have active routes, network destination, by default 0.0, netmask 00, gateway 10.01, interface 10.0.0.57, metric 25, and along 1, 2, 3, 4, 5, 6 others. The first portion of this output shows 7 different network interfaces that may be used for carrying network traffic. The first is the virtual loopback interface. The next is a Wi-Fi wireless interface. The third is a wired Ethernet interface that is disconnected. The fourth is another loopback interface, and the next 3 are used as part of the non-standard intra-site automatic tunneling address protocol eSATAP. eSATAP is used in supporting IPv6 hosts separated by an IPv4 network. Moving on to the routing table, we see that there are 7 entries that could be used to determine where broadcast traffic should be sent. The first entry is the default route, mask 0.0.0.0, so it matches any destination. This could be used by broadcast directed beyond the local network. If such facility were enabled, the type of directed broadcast which travels beyond the local network is usually disabled by routers to avoid a number of security problems as suggested by RFC 2644. The next 3 entries are the directed subnet. So that is actually for the default mask. It's actually used to determine where broadcast traffic should be sent. Beyond local network, but this is usually disabled. So the next 3 entries are directed, because again broadcasts are rarely used in the internet beyond local LAN. The next 3 entries are directed subnet addresses associated with 3 interfaces having IPv4 addresses 10.0.0.57, comma 127.0.0.1, comma 169.254.57.243 respectively. The last two are software loopback interfaces. These entries shows how Windows expresses a direct subnet broadcast route as the network prefix combined with all 1 bits in the host part as the destination n/32 or 255.255.255.255 subnet mask. So this route table or routing table of the router explain much of what we have discussed. The gateway column indicates on link, so traffic is delivered using direct delivery and the interface identified in the interface column. In these cases, there is not more than one match for each subnet directed broadcast, so the metric column is not consulted. The last three entries are routing entries for the limited broadcast address 255.255.255.255. In some ways, this address acts like a multicast address because network. Thus, it is not immediately obvious which interface should be used for sending traffic destined for the limited broadcast address. Unfortunately, Section 3.3.6 of the House Requirements RFC 1122 provides little guidance. There has been discussion on whether a datagram address to the limited broadcast address ought to be sent from all the interfaces of a multi-home host. This specification takes no stand on the issue. As a consequence, the way outgoing traffic to the limited broadcast address is handled is operating system specific. Most systems pick a single broadcast capable interface on their routing table to use for sending such traffic. Linux and FreeBSD behave this way. FreeBSD actually converts the limited broadcast address into a subnet directed broadcast address of the primary first configured interface, although an application can disable this behavior using the IP_1B cast API option. Windows, for example, has behaved differently in different versions. Up to Windows 2000, limited broadcasts were forwarded over multiple interfaces. With Windows XP and later, the default behavior is to send over a single interface. In this example, there are multiple possible matching routes for such traffic, so the entry with the lowest metric interface 10.0.0.57 is used. Multicasting. Fundamentally, this is accomplished by either having the sender indicate the receivers or instead having the receivers independently indicate their interest. So it's either the receiver or the sender. It's kind of like the mechanics that we have as well for broadcasting and multicasting. But here, we have two options, the sender could choose and the receiver could choose as well. The network then becomes responsible for sending traffic only to intended or interested recipients. Implementing multicast is considerably more challenging than broadcast because multicast state information must be maintained by host and router as to what traffic is of interest to what receivers. So you actually have to configure like a one-to-one mapping, kind of like a socket, IP plus port, or how how would your OS actually map to an actual broadcast, what broadcast, and you have to save the state, and you also have to delete. Unlike with broadcast, though you may have multiple addresses that is mapped to a broadcast address within your LAN, it's still the same. You don't need to change the state because it's burned into your NIC. In the TCP or IP model of multicasting, Receivers indicate their interest in what traffic they wish to receive by specifying a multicast address and optional list of sources. This information is maintained as soft state, see chapter 4, within host and routers, meaning that it must be updated regularly or it will time out and be deleted. When this happens, delivery of multicast traffic either ceases or reverts to broadcast. IP multicasting provides a more efficient way to carry out the same types of tasks. If IP multicasting is used properly, one of its property is only those hosts involved or interested in the communication need to process the associated packets. Traffic is carried only on those links where it will be used, and only one copy of any multicast diagram is carried on such link. So whenever you're sending it, you only have one copy instead of having duplicate. To make multicasting work, applications that wish to involve in a communication require a mechanism to notify their protocol implementation of their desires. The host software can then arrange to receive packets matching the application's criteria. So you need a protocol or a way to notify, or the application need to notify the protocol of their desire. So the OS needs to actually program it using IP, right? So the host software can then arrange to receive packets matching the application's criteria and protocol. It could be a protocol as well, since protocol is also mapped to IP then frame. IP multicasting originated using a design based on the way group addressing works in link layer network such as Ethernet. So it actually got its idea with Ethernet and how it groups the interfaces via VLAN. Remember how you group interface via VLAN in previous video? It's almost the same as that. In this approach, each station selects the group address for which it is willing to accept traffic, irrespective of the sender. This approach is also sometimes called any source multicast because of the sensitivity of the sender. So you would notice that an address like could have many hosts, right? So that's what any source multicast, meaning you don't care about the host. There's another type. As IP multicasting has evolved, an alternative form that is sensitive to the identity of the sender called source-specific multicast (SSM) has been developed that allows end stations to explicitly include or exclude traffic sent to a multicast group from a particular set of senders. So here you're gonna choose what actually host within that subnet you want to receive to. The SSM service model is easier to implement. So this model is easier to implement than ASM, primarily because in wide area multicasting, it is easier to determine the location of a single source than the location of many sources. So it also has this principle of NAT, where you need to actually traverse it to get a peer-to-peer connection. You need the actual IP of the host you want to talk to. So it's the same principle. That's why it is recommended the SSM, or specifying the actual host you want to send to, rather than blindly sending it to to their subnet. In the local area, however, much of the machinery involved in supporting either ASM or SSM is identical. So we treat them together and explain a few differences when they are important. We begin by investigating how IP multicast traffic make use of MAC layer multicast addresses on multicast capable IEEE LAN technology. So how do actually the layer 3 traffic make use of the MAC layer or the layer 2 on multicast capable IEE LAN technology. So there's a supported technology that support the multicast. How does it actually map from layer 3 to layer 4? Converting IP multicast address to 802 MAC/Ethernet address. When using unicast addresses on Ethernet-like networks, ARP, see Chapter 4, is usually used to determine a local destination MAC address given to IPv4 address. Ideally, we would not have to use a protocol message to determine the appropriate MAC address, but could instead simply map an IP multicast address directly to some corresponding MAC address. So it's the same with broadcast. Ideally, we want to know the the multicast address. To see how this is done, we shall focus on IEEE 802 networks, especially Ethernet and Wi-Fi. So remember, the key principle is it needs to somehow program by the OS and it needs to save state. So let's look at how it is being done by two technology, Ethernet and Wi-Fi. These networks represents the most common types of networks where IP multicasting is used. We will first discuss how the mapping works with IPv4, then move on to slightly different method used with IPv6. To carry IP multicast efficiently on a link layer network, there should be a one-to-one mapping between packets and addresses at the IP layer and frames at the link layer. So to be able to carry that in layer 2, there should be one-to-one mapping on layer 3 and the layer 2 and the sender and the host of the one that's communicating. With it, IANA is given the right to use group multicast MAC addresses starting with 01:00:5E as well as unicast addresses starting with 00:00:5E. This prefix is used as the high order 24 bits of Ethernet address, meaning that this block includes unicast addresses in the range 00:00:5E, 00:00:00 through 00:00:5E FF:FF:FF, and group addresses is the range 01:00:5E, 00:00:00 through 01:00:5E, FF:FF:FF. The IANA allocates half of its group block to identifying IPv4 multicast address on IEEE 802 LANs. So it allocates half of that address to support IPv4. That's the class D we have before. So remember, we turned to CIDR. This means that the Ethernet address corresponding to IPv4 multicasting are in the range 01:00:5E, 00:00:00 through 01:00:5E, 7F, FF:FF. So this will be the allocated multicast address for the MACs that will be chosen to support it or to subscribe to it, the source and sender that will subscribe to it. The notation here uses the internet standard bit order as the bit appears in memory. This is what most programmers and system administrators deal with. So the mapping of IPv4 addresses to their corresponding IEEE 802 style link layer addresses can be seen in figure 9.2. The IPv4 to IEEE 802 MAC multicast address mapping uses the lower order 23 bits of the IPv4 group address as the suffix of a MAC address starting with 01:00:5E. Because only 23 bits of the 28 group address bits are used, 32 groups are mapped to the same MAC. Recall from chapter 2 or in the previous video that all IPv4 MAC addresses are contained within the address space from 224.0.0.0 to 239.55.255.255, formerly known as Class D address space. So this is where it get it from. All such addresses shares a common 4-bit sequence of 1110 in the higher order bits. Thus, there are 32 minus 4 equal 28 bits available to encode the entire space of 228 equals 268 435 456 multicast IPv4 addresses, also called group IDs. For IPv4, the IENA policy of allocating half of its group addresses for use in supporting IPv4 multicast means that all 268, 435, 456 or 268 million IPv4 multicast group IDs need to be mapped into a link layer address space containing only 223 equal 8,388,608 unique entries. The mapping therefore is non-unique. That is, more than one IPv4 group ID is mapped to the same MAC layer group address. So you could have more of this IP address that are technically sending to the same group. So there's multiple IPv4 address that's sending to the same MAC layer group. So let's say you group this MAC layer to VLAN to be sent to as your recipient for your send. You could have multiple broadcast or IPv4 multicast address to be able to send that. So you can like chop your packet. Some are coming from this address or some coming from this address, but all of that multicast will only have one copy in one link, but all of them will receive the packet. Specifically, 228/223 equal 25 equal 32 distinct IPv4 multicast group IDs are mapped to each group address. So you have 32 IP or layer 3 IPv4 multicast ID to each group. So imagine it is being handled by 32 IP address. For example, both the multicast address 224.128.64.32 hexadecimal E0 .80.40.20 and 224.0.64.32 hexadecimal E0.00.40.20 are mapped into Ethernet address 01:00:5E:00:40:20. So in this host or recipient, you have two ways to route into it. You have two layer 3. For IPv6, the 16-bit OUI hexadecimal prefix is 33:33. This means that the last 32 bits of the IPv6 address can be used to form the link layer address. Thus, any address ending with the same 32 bits maps to the same MAC address, see figure 9.3. Given that all IPv6 multicast address begins with FF, and the subsequent 8 bits are used for flags and scope information, this leaves 128 minus 16 equal 112 bits for representing 2112 groups. Thus, with the 32-bit of MAC layer address available to encode these groups, there can be as many as 2112/232 equal 280 groups that map to the same MAC address. Here in figure 9.3, the IPv6 to IEEE 802 MAC multicast address mapping uses the low order 32 bits of the IPv6 multicast address as the suffix of a MAC address starting with 33:33. Because only 32 of the 1112 multicast address bits are used, 280 groups are mapped to the same MAC layer address. Examples. In previous example, we used a subnet broadcast address to determine all the hosts on the local subnet that would respond to a broadcast ICMPv4 echo request message. Here, because we can use multicast addressing to determine hosts that offer a particular service, we can send an ICMPv4 echo request to those hosts that responds to multicast DNS (MDNS) address 224.0.251. So in Linux, if you ping 224.0.0.251, you get this. 64 bytes from 10.0.0.2, 64 bytes from 10.0.0.11, 64 bytes from 10.0.0.120. Here, host 10.0.0.2, 10.0.0.11, and 10.0.0.120 all respond, indicating that they are subscribed to the MDNS group. Notice that these hosts are not the same ones that respond when we use the broadcast address of 10.0.0.127. This is not so surprising, as not all hosts support the MDNS protocol. Note, Multicast DNS. MDNS is a service designed to support zero configuration, effortless system and device configuration. MDNS has been supported on Apple systems where it is part of Bonjour. Microsoft has promoted an alternative protocol that includes similar feature known as Think Local Multicast Name Resolution, LLMNR, in RFC 4795. Neither protocol is currently an internet standard within the ETF, but at present, MDNS enjoys a longer history than LLMNR. See Chapter 11 for more details. For IPv6, we can perform a similar operation using an ICMP v6 echo request. Ping 6 dash capital I ETH0 FF02 colon FB. So as you can see, we ping that and we received 64 bytes, only 164 bytes from FE80 colon 217 colon etc. ICMP sec1 TTL 64 time 2.76 ms, and we have FB ping statistics. So note that this case, we provide the outgoing interface as input to the ping6 program. This allows the program to select the appropriate outgoing IPv6 address in Windows XP. As we can see in figure 9.4, the address selected is a link local address associated with the ETH0 device. Figure 9.4, an ICMP v6 echo request message is sent from a link local unicast address associated with the ETH0 network interface to the multicast FF02 colon FB. The reply includes the sender's IPv6 link local IPv6 address. The packets are identified as ICMP v6 echo request or reply messages with the identifier field set to 0x1D47 and sequence number field set to 1. The source IPv6 addresses are linked local in all cases. The destination address of the request is the multicast address FF02 colon FB, which is mapped to the MAC address 33 colon 33 colon 00 colon 00 colon 00 colon FB. The echo reply message is sent directly to the link local IPv6 unicast address of the sender, FE80 colon 208 etc. from the responder's link local unicast address. Note that the sender of the echo reply message arranges to use a source IPv6 address of the same scope.